Welcome to qnawire.
Hi, in the given problem, here this is the direction of magnetic field like this. And in this magnetic field, there is a loop whose end side view is visible to us. And the plane of the loop is making an angle of 60 degree with the direction of this magnetic field. So if we draw a normal at the plane of this loop, this normal drawn at the plane will be making an angle of 30 degree with the direction of magnetic field. The radius of this loop has been given as 75 centimeter, or we can say this is 0.75 meter, and the magnetic field variable, which is variable with the time, has been given as 1.4 into e raised to the power minus 0.057 t, where this t is the time, Tesla. This is the time varying magnetic field given to us. So in the first part of the problem, first of all, we will find the total magnetic flux linked with the loop. So using expression for the flux, it becomes B dot A, the dot product, the scalar product of magnetic field with the area of the coil. So it comes out to be B times A into cosine of angle between area vector and magnetic field, which is 30 degree. So we put the values of magnetic field and area, and the magnetic field is 1.4 times E raised to the power minus 0.057 t, as the magnetic field is variable with the time, and the area is pi 0.75 to the whole square multiplied by cos 30 degree. So when we calculate all these values and multiply them with the 1.4, we get this to be 2.14 multiplied by e raised to the power minus 0.057 t. So this is the expression for this magnetic flux linked with the loop in terms of time. So the EMF induced at any instant in this coil will be given by using Faraday's laws of electromagnetic induction as negative of the time rate of change of this magnetic flux, d phi by dt, or we can say this minus 2.14 will come out as a constant, so it will remain the differentiation of e raised to the power minus 0.057 t. So this differentiation will come out to be minus 2.14 into e raised to the power minus 0.057 t as it is. Then the differentiation of this power, which comes out to be minus 0.057. So when we multiply them, this EMF, the value of this EMF comes out to be 0.122 times e raised to the power minus 0.057 t. So this is the expression for EMF induced with the passage of time. Now, in the second part of the problem, initially we have to find the initially EMF induced in this coil. So if we look for the initial, the time comes out to be 0. So the initial EMF E naught will be given by 0.122 multiplied by e raised to the power minus 0.0577 into time, which is 0, means it will become e to the power 0, which will become 1. So finally, this initial EMF induced will come out to be 0.122 volt. Now we have to find the time in which the EMF induced will reduce to 1/10 of the initial EMF. Means that EMF, instantaneous EMF, should be 1/10 of the initial EMF. Means it should be 0.122 divided by 10, or we can say this is 0.0122 volt. So using the equation, this becomes 0.0122 is equal to 0.122 times e raised to the power minus 0.057 t. So e to the power minus 0.057 t will come out to be 0.0122 divided by 0.122, or we can say this is 1/10. So this reduced to minus 0.057 t is equal to natural logarithm of 1/10, or we can say natural logarithm of 0.1. So finally, the expression for time comes out to be natural logarithm of 0.1 divided by negative of 0.057. So when we solve this, the time comes out to be 40.4 seconds. This is the time in which the EMF induced reduced to 1/10 of the initial EMF induced. Now, in the third part of the problem, we have to find the direction of current induced in this loop. As when we see at the coil from upward, the direction of EMF is upward and it is decreasing. So the magnetic flux is upward decreasing. So as per Lenz's law, the induced magnetic flux should be upward increasing. To oppose the reason behind its induction, it should be upward increasing. So this upper phase should start behaving like North Pole, or we can say the direction of current induced should be counterclockwise. Thank you.